we will continue with our DC chapter and DC motor chapter, and we will finish this chapter today. So last lecture we covered the torque speed characteristics. We defined what is meant by torque speed characteristics, and then how we can use this knowledge to do speed control of DC motors. And in speed control in DC motors, we had three types of speed control: the armature voltage control, and the armature resistance control, and the field control. So today we will continue the speed control of DC motors, and we will solve a couple of problems before going to DC motors, series motors, and examples. Now let's start by a quick revision for the speed control and the torque speed characteristic. So the torque speed characteristic for DC motors, and here we are when we are covering motors, we are covering shunt, separate, or permanent magnet. These three motors have the same characteristic and the same type of speed control. The series machine is a little bit different, as we will see today. So the torque speed characteristic for shunt motor, as we did the proof, that omega, or the speed, equal to VA divided by K motor IF minus RA divided by K motor IF all squared multiplied by T developed. This equation is the equation that relates our speed to the torque, or it is a torque speed characteristic. Now, to do speed control, we said that we have three variables that we can change. So we can change VA, or we can change RA, or we can change the value of IF. So we have three types of control, but these three methods of control can be classified into two categories. The first one is armature control, so you do the control from the armature, and the second one is the field control. And under the armature control, we can do armature voltage, or we can do armature resistance. And for the field control, just we are changing the field current. So these are the three types of controls that we have. So it's changing VA, it's changing RA, or it's changing IF. And as we said, we can take VA down or reduce VA if we started from rated value, and we can increase RA because we are adding an external resistance, and we can reduce IF given that we started at the rated values. And these are the three control variables we have, or these are the two categories we have: the armature control and the field control. As we covered last time, that the armature control can control speed below rated, so the speed can be controlled from 0 to N rated, and the field control is used to control the speed above rated, so the speed can go from N rated, and theoretically we can reach infinity. So if we have a scale here, and our x-axis here is speed, and this point here is N rated, so below N rated, so from 0 to N rated here, we will use armature control, and to control the speed above N rated, we will use field control. So if we need to sketch, for example, the field current, so when we do armature control, the field current will be constant, and when we do field control, we'll start to decrease the field, and when the field current reaches 0, the speed reaches infinity. Now if we need to sketch the armature voltage, so for the armature control, we'll change V armature from 0 up to V rated, and here this is IF rated, and then after V is V rated, V armature will be constant. So as you can see here in field control, the armature is constant, and in armature control, the field is constant. And this graph shows us how we can do armature control and field control. The curve for the field is the same as the curve for the torque. So when we do armature control, the torque will be constant, and when we start to do field control, the torque will decay, and the torque will decay, but we are getting higher speed. So if we need to sketch the power of the machine, so the power is torque multiplied by speed. For armature control here, your torque is constant while your speed is increasing. So if we sketch the power will be increasing. And here the torque is going down while the speed is increasing. If we sketch the power will be constant. So these are the important variables for the different control methods. So we can name that the armature control, we can name this as constant torque, while the field control, we can name it as constant power. So if you can see here that the torque is constant in armature control, while the power is constant in field control. So we can give the name of constant power to the armature control and to the field control. So we give the constant power name to the field control, and we give the constant torque name for the armature control. So if you need to control the speed while keeping the torque constant, we do armature control. If we need to control the speed while we need to keep the power constant, we will do field control. So these are the two types or the two classes of control: armature control and field control. Let's add another page here. So if we have 200 volt, 1200 RPM motor, and we need to control the speed of this motor, and we need to do speed control, or we want to do speed control. So to control the speed from 0 to 1200 RPM, we can do this by controlling the voltage V armature from 0 to 200 volt. So if we change the voltage V armature from 0 to 200 volt, we will change the speed from 0 to 1200 RPM. And this type of control is armature control. So if the question asking you, we need to control the motor so that the speed is 900 RPM. So this 900 RPM is less than 1200 RPM. So the technique we are going to use, or the method we are going to use, will be armature control, armature voltage control. But if the question is asking you to control the motor, so the speed is 1450 RPM. Now this 1450 RPM is larger than the 1200 RPM, the rated one, the maximum that you can get from rated values. In this case, we will do field control. So sometimes in the questions in the exam, sorry, you will have to determine which speed control technique you are going to use. And the test here you will do is comparing the value given with the rated speed. If the value below rated speed, we do armature control, and if the value is larger than rated speed, we do field control. And when we do armature control, IF is constant and equal to rated field current. And when we do field control, armature voltage constant. And equal to rated armature voltage. So please don't forget these notes. So when we do armature control, the field will be constant, and the field will be constant at its maximum value. And when we do field control, the armature voltage will be constant, and the armature voltage will be constant at its rated value. Okay, so when we do armature control, in this case, we have to keep field constant. And when we do field control, in this case, we have to keep armature constant. And we keep the armature constant equal to the rated value. Here we keep the field constant equal to the rated value. We will do armature control to change the speed from 0 to n rated, and in this case V armature will change from 0 to V armature rated. Once your voltage reaches the rated and your speed is reached the rated, you cannot increase the speed anymore. To increase the speed more, you need to switch from armature control to field control. In this case, V armature will equal to V armature rated, and you will start to play with the field current. So the field current will change from I field rated to 0, which will give you speed from N rated and can go theoretically up to infinity. And these are the two types of speed control we have for DC machines. Now let's do one example here. So we have a separately excited DC motor. So this example is from our first lecture, and it was left as a homework. Okay, so let's do it. Sorry. So we have a separately excited DC motor. As we said, that the DC shunt, separate, and permanent magnet, they have the same characteristic, same torque speed, same methods of control. So we have a separately excited DC motor has the following parameters. Field resistance is 250, armature resistance is 0.03. The terminal voltage is 250 and the field voltage is 250. So if we sketch the circuit here, we have a DC separate, so the field is separate from the armature. EA, RA, IA, RF, VF, VA. So here we have 250 volt field, and RF is 250 ohms, RA is 0.03 ohms. Now initially, so this is a condition, or this is a case. The machine runs at 1000 RPM and the voltage is 250 volt and the armature current is 120 amperes. So we can write case 1, the initial case, that I armature equal to 120 ampere, V armature equal to 250 volt, and N equal to 1000 RPM. And we can name these as case 1. Then what happened? The load torque dropped to 50% of its original value. So we have case 2. In case 2, T2 equal to 0.5 T1. The torque dropped by 50%. And we need to find the speed of the motor if the terminal voltage changed to 200. So in case 2, we changed the armature voltage. So changing the armature voltage means we are doing armature voltage control or we are controlling the speed using an armature voltage. So in this case here, we have V armature 2 equal to 200 volt. So these are the given data which we need to use. We mentioned for DC motors, we will be given one case with all the values, and we will be given another case with some missing data. And the idea is to make the first case as full as we can. Then we use the ratios between the two cases. And the ratio between the two cases will be the ratio between the EMF 1, EA1 and EA2, and T1 and T2. So if we write KVL for equation 1, so if we go to case 1, we have VA1 equal to 0.03 IA1 plus EA1. So VA1 is 250 equal 0.03, IA1 is 120 plus EA1. So we can get EA1 as 247.6. Let's check this. So EA1 equal 246.4 volt. So from this equation we got what is the value for our EA1. So once we have our EA1 as 246.4, we have all the values for case 1. Usually we don't need to calculate the torque because usually the relation between the two torques are given, so we don't need to calculate each torque separate. So here we don't need to calculate EA1. So as we can see that at case 1 we know IA1, we know VA1, we know what is N1, we know what is EA1. Also we can calculate I field 1. So I field 1, the voltage here is 250, the resistance is 250. So IF1 is 250 divided by 250 equal 1 ampere. Now we can go to case 2. So we know that in case 2, T2 divided by T1 equal to 0.5. And we know that V armature 2 equal 200 volt. And we need to calculate what will be the speed. And to calculate the speed, we said whenever you are asked about speed, think about EA. So the question is, we need to calculate EA2. If we have EA2, we can simply calculate our speed N2. So let's add a page here. So what we can say EA2 equal to VA2 minus 0.03 IA2. So EA2 equal to 200 minus 0.03 IA2. This is one equation. So in this equation we have two unknowns. We have EA2 and we have IA2. So the question is, what is IA2? And whenever you need to calculate current, you have to think about torque. So we have T2 divided by T1 equal 0.5, which equal to IF2 divided by IF1, I armature 2 divided by I armature 1. And we have I field 2 over I field 1 equal 1 because the machine is connected as separate. And if the machine is separate, if the load here changes and the voltage here changes, there is no link between the two circuits. The field circuit here is separate from the armature circuit. So when the load torque here dropped to 0.5 of its value and the voltage here dropped to 200 volt, this will not affect the field circuit here. So the field circuit here is separated. So here we can say that IF2 over IF1 equal 1. So we can calculate IA2 as 0.5 IA1. So this equal to 60 amps. So we can substitute in equation 1 to get IA2. So IA2 will be 200 negative 0.03 multiplied by 60 amperes. So this will give us 198.2 volt. Once we have EA in case 2, we can calculate the speed in case 2. So the speed in case 2, EA2 over EA1 equal to IF2 divided by IF1, N2 divided by N1. And we have that IF2 divided by IF1 is 1, so we can substitute here as 198.2 divided by EA1 is 246.4 equal to N2 divided by N1 is 1000 RPM. So the only unknown in this equation is N2. So we can calculate N2. So N2 equal to 804.38 RPM. So here when the torque dropped by 50% and the voltage reduced by to 200 volt, the speed will go to 804.38 RPM. So please add this third part to the question and try to solve it. See if the load torque dropped to 60% of its initial value, calculate V armature to keep the speed unchanged. So this is the third part. What if the torque dropped to 60%, but in this case you are not given VA, you are given the speed, that the speed is not changing, we need to keep the speed. What will be V armature in this case? Let's name it V armature 3. So please try to solve this problem before our next lecture. Now let's add another page here. Now we will solve another problem here. So what we have here, we have a 220 volt DC shunt motor, has an armature and field resistance of 0.2 and 220. The motor is driving a fan load, so the torque is proportional to N square. The machine is running at 1000 RPM and takes 10 ampere from the supply. We need to highlight that this current is from the supply, not the armature. Now we need to calculate the new speed and the new armature current if an external armature resistance of 5 ohms is inserted to the armature circuit. So what is the type here? This is an armature resistance control. So we inserted a resistance in the armature, so we are expecting our speed to go down, because when you insert resistance in the armature, you are increasing the losses, you are decreasing the current, so the speed should go down. And in the question here it says neglect armature reaction and saturation. Already we assume all our circuits working at linear, so when we neglect saturation, this is where we removed phi and we substituted instead of phi with IF. But what is the armature reaction is? Do you know what is the armature reaction is? So if you don't know what is the armature reaction is, you already neglected it. So just don't ask me in the exam, okay? So the armature reaction, we didn't study the armature reaction here, and it needs too long time to cover this armature reaction, and it is not important to analyze the circuit if you don't know what is the armature reaction is, because usually we neglect it. Now, how we will solve this circuit, or how we will solve this problem? So we have a DC shunt machine, so let's sketch the machine. This machine is driving a fan load, so here's the torque is proportional to speed square. Here we have EA, RA. This RA is 0.2, RF is 220 ohm, the source here is 220 volt, and the machine was running. Then we inserted here a 5 ohm resistor, and we need to see what will be the speed. As we mentioned that we will divide our problems into cases, and we need to see one full case and then cases with some missing data. Okay, so let's start by defining the cases. Case 1. So case 1, the machine was running at 1000 RPM. So this is N1. And the machine takes 10 ampere from the source. So I source 1 equal 10 amperes from the source. So this is the data given, and the voltage here is given as 220 volt. So we need in our circuits I armature, not I source. So how we will convert the given source current into an armature current? So we can calculate I field 1, because we are given the source and we are given RF. So I field 1 equal 220 divided by 220 equals 1 ampere. And I source 1 is I field 1 plus I armature 1. This is KCL at this node. So we can calculate I armature 1 to be 9 ampere. So we have I armature 1, we have I field 1, we have N1. What else we can get? We can get E armature 1. So E armature 1 equal V armature 1 negative R armature 1 I armature 1. So E armature 1 equals to 220 negative R armature here is 0.2 multiplied by 9. This equals to 220 minus 9 multiplied by 0.2. This equals to 218.2 volt. So we have here the speed N, we have IF, we have IA, we have E. We can calculate T developed by using EAIA equal T developed omega, but as we mentioned, usually we use the torque ratios, so we don't need to calculate the torque as a value unless it is required in the question. Now let's go to case 2. So what is given is case 2. We given in case 2 that we inserted 5 ohm in the armature circuit. So this is the only change between case 2 and case 1, that you inserted here 5 ohm resistor. This means the circuit is still the same. So we still have I field 2 equals to I field 1 equals to 1 ampere. So we didn't change the field circuit, so the field current is still the same. Also, we didn't change the source voltage. So V armature 220 equal to E armature 2 plus R armature now is 0.2 plus 5 and I armature is I armature 2. So the only change between this equation here, KVL in this equation, and KVL in our first equation, that in the first equation the resistance was 0.2 and here the resistance is 0.2 plus 5. And I armature 2 is not the same as the first case because the torque will change. So we can write down this equation as 220 equal to E armature 2 plus 5.2 I armature 2. This is the equation we have. In this equation, we have E armature 2 as unknown, we have I armature 2 as unknown. Now we need to get more equations to be able to solve this problem. So how we'll get more equations? To get more equations, we will use the relation between EA2 and EA1 as IF2 divided by IF1, N2 divided by N1. So IF2 divided by IF1 is 1, E armature 2 is unknown, E armature 1 was 218.2, N2 is unknown, N1 is 1000 RPM. So we can write down here that E armature 2 equal to 0.2182 N2. And this is our second equation. Also, we can write down T2 divided by T1 equal to IF2 divided by IF1, I armature 2 divided by I armature 1. And I field 2 divided by I field 1 is 1 because we didn't change the field circuit. We don't have T2 and we don't have T1. But here, it is given that this machine is deriving a fan load. And it is given that the torque is proportional to the speed squared. So what we can do here, we can write here N2 divided by N1 all squared. So here we have I armature 2 divided by 9 equal to N2 divided by 1000 RPM squared. So we have here I armature 2 equal to 9 divided by 1000 squared multiplied by N2. This is equation 3. Now we have 3 equations, equation 1, equation 2, equation 3. And we have 3 unknowns. We have N2, we have EA2, we have IA2, we have N2, EA2, IA2. So we can substitute the three equations together and solve them to get the three variables. So the idea here is to keep N2 as our variable and rearrange the equation. So we can substitute for EA2 here, and we can substitute here for IA2. So we have 220 volt equal EA2 plus 5.2 IA2. So 220 equal to 0.2182 N2 plus 5.2 multiplied by 9 divided by 1000 squared N2 squared. N2 squared. Now we can rearrange this equation as 5.2 multiplied by 9 divided by 1000 squared N2 squared plus 0.2182 N2 minus 220 equals 0. And we can solve the second order equation using the calculator directly, which will give us two values for N2. One of them will be accepted and one will be rejected, and the one will be accepted is the logical one or the physical one. So we know that the speed will go down from 1000 RPM. So we are expecting N2 to be between 0 and 1000 RPM. So this will be the one that we will accept, and we will reject the other one. So here we need to solve this equation. So let's solve it using the calculator. So we solve this using the calculator. So N2 equal to 852.407 RPM, and N2, the other solution, will be negative, so I will just drop it. So we have N2. Once we have N2, so we can go back and calculate IA2 here from this equation. So we have 852.107 multiplied by 9 divided by 1000 square. So IA2 is 7.6 amperes. So now we get what is the value for IA2. So 9 divided by 1000 multiplied by 852.107. So we can get IA2. So here we have the speed N2 and the speed N2 here. So we will accept the speed range is between 0 and 1000 RPM. This value here is negative, that's why we rejected it. And this problem is how we can do speed control using armature resistance. And this technique is not recommended because it increases your losses. So I will stop the lecture here and we can continue